Welcome to this introduction to differential geometry in Sage Math, or Sage for short. In this video I will assume some basic familiarity with Sage, so you should know how to install it and how to use its basic functionality. So let's dive right away into differential geometry. I have prepared a Jupyter notebook for you to demonstrate some of Sage's capabilities when dealing with differential geometry. This will by no means be comprehensive. There are a lot more things that you can do. I recommend to look at the Sage Manifolds documentation for that. So I just want to give you some working knowledge so that you can start and explore things for yourself. The first thing is that I set the display engine to LaTeX, because then this will make the output look a lot nicer. All right, so let's declare a manifold. So here I invoke the manifold function. M is put to the manifold function applied to three arguments in this case. The first argument, the number 3, tells Sage that it's a three-dimensional manifold. The second argument, this string M, is the mathematical name for the manifold. So this is not to be confused with the variable M here. So this is the Python variable representing this object in the computer, while the string M is the mathematical name for the manifold. And the third argument, start index equals 1, tells Sage to start the numbering of the coordinate functions with the index 1. By default, it starts with 0, as is usual in Python. That might be a good convention for Lorentzian manifolds, but for Riemannian manifolds, I prefer to start the numbering of coordinate functions by 1. All right. So I've declared this manifold. Now if I print M, then I get a short description of the object that I have, namely a three-dimensional differentiable manifold M. If I change the mathematical name to something different like H, then and I printed it, then Sage would tell me that the Python variable M stands for the three-dimensional differentiable manifold H. You could actually do something even more sophisticated. Namely, when I just call M, then I get the LaTeX rendering of the name of M. But I could use the full power of the LaTeX rendering engine by adding another name here. This is also a mathematical name of the manifold, but now used for, now it can be any LaTeX expression. So let's say take the mathematical blackboard font of H. And to indicate the dimension, I add an upper index 3 here. Now if I call that, oh, now I get an error message. And the reason is that the string that I put in here contains a special character named the backslash. And so that confuses Sage. So I have to tell it that the string is to be taken as it is, and the backslash is not to be considered as a special character. So I put an R in front of it, which tells now Sage that this is a raw string and just take it as it is and put it to the LaTeX engine. Now everything seems fine. So print M still gives me the mathematical name H, and now if I call it, the LaTeX expression is used to display the manifold. But let me go back to the convention that this is the same, otherwise I might get confused later. Okay. Often you want to loop over all coordinates of your function. For this, it's good to have a list of all the coordinate numbers, and this list can be obtained by the method iRange. So if I look at this list that iRange gives me, then this is the list of coordinate functions. You have the first one, the second one, the third one. Without the start index argument in the declaration of M, the list would have been 0, 1, and 2 rather than 1, 2, and 3. In order to specify a manifold, we need to define charts on the manifold. So we can declare several charts on the manifolds and relate them by transition functions, as we will see. So let's start by declaring a first chart on the manifold. So for this we use the chart method. So we declare a chart of the manifold M, and I call this chart std. So this is just for reminding me that this will be my standard chart. You could call it anything here. And this expression xyz tells Sage that the coordinate functions for this chart will be called x, y, and z. And the string inside the chart function tells Sage that there's a restriction on the variable z, namely the variable z has to lie between 0 and plus infinity, so it has to be positive. And there are no restrictions on the chart functions x and y. Okay, so now I've declared a chart, and I can display the chart. So then this tells me, okay, we have a chart defined on the whole manifold M. Often it will only be defined on an open subset, but in this case it's defined on the whole manifold, and the chart functions are called x, y, and z. I can also access these three coordinate functions individually by calling them by their corresponding numbers. So first standard chart function is x, second one is y, and the third one is z. If you want to have them all at once, you can use the colon operator, and then you get a tuple with all three coordinate functions in this. Okay, now we can declare functions of the chart coordinates, and this is done by the method function. So if I want to declare a function of the coordinates with respect to this first chart, and so far we have no other chart, but if we want to declare a function of the coordinate functions x, y, and z, we can do this with the function method. And as an argument, I insert the expression that should describe the function. So now f is a function of the coordinate variables x, y, and z, and the result will be given by x plus y squared plus z cubed. We could display this function, so then it will remind us of the function that maps x, y, and z to this expression. And we can also evaluate it on particular values for my functions x, y, and z, let's say on 633, and well, the result we get is 42. If you have a function defined and you want to get back the expression that it defines, for example, in order to use this expression in other Sage methods or functions, then you can invoke the expression method to f, and this will give you back the expression that you used to define your function. Okay, now we have declared a manifold, we have declared one chart, and we have defined one function of those chart coordinates. Let's introduce a second chart on the manifold. In this case, the second chart will not be defined on the whole manifold, so we first define an open subset U, on which we will then have the other coordinate functions. And I will sort of define kind of polar coordinates in the xy plane, and therefore I want to remove a ray from the xy plane in order to make polar coordinates well defined there. In fact, the set U will be the complement of the region of the ray which is given by y equals 0 and x non-negative in the xy plane. So the complement of this set is given by the set of x, y, and z's where y is non-zero or x is negative. And this is encoded in this expression. We have these two conditions, and the parentheses mean that these two conditions are combined with an or statement. If instead you want to combine several conditions with an and statement, you can do that too. Then you just have to replace the parentheses by square brackets, like here. Okay, so let's declare an open subset of the manifold. The Python variable will be u. The mathematical name for it will also be given by the string u. And the set is defined in terms of the standard coordinates. We have no other coordinates so far. By these two conditions, y is not equal to 0 or x is negative. Okay, let's define that. And so we can take the standard coordinates and restrict them to this set u. And we call this new chart with the same coordinate functions but restricted to u by std u. So let's do that. So we have now a new chart. It's a new chart defined only on the subset u, but with the same coordinate functions. But that's not interesting. We want to have other coordinate functions. And what I'm doing here is in the xy plane, I'm introducing polar coordinates given by radial distance from the origin and an angle, theta. And here there's a misprint. The third one is a t. And the third coordinate is a t, which will be related to our coordinate z via an exponential or logarithm. So I define a new chart now only on u, which I call polar. The new coordinate functions will be r, phi, and t. Should I write phi here too? R, phi, and t. And so the restrictions are that r is positive and phi lies between 0 and 2 pi. And there's no restriction on t. Okay, so this is a new chart also defined on u, but now with coordinate functions r, phi, and t. Again, I can access those coordinate functions by their corresponding numbers. So that would be phi and t. And these declarations of coordinate functions contain some restrictions on those functions, and Sage remembers those. So if we call assumptions, then we see all the assumptions that we have made on our function so far, namely that x is real, y is real, z is real, and z was declared to be positive. Now r is real and positive, the angle phi is real, it's positive and less than 2 pi, and t is real. And these assumptions are remembered by Sage and used in simplifications. So for example, when I square r and take the square root again, then in general, if I only knew that it's a real variable, then I would get the absolute value of r. But since r is supposed to be positive, Sage can simplify this to r itself. So these assumptions that we made are used in simplifications. I need to tell Sage now how the two charts are related. So the x, y, and z coordinates are related somehow to the polar coordinates, and I have to tell Sage how they are related. And this is done by the next command. So I define a transition map from standard chart on U to polar chart also on U. And this list here gives the coordinate functions of the standard chart in terms of the coordinates of the polar chart. So you see here the expression for polar coordinates in the xy plane, and t and z are related via an exponential. So let's do that, and here we have the relation. X is r cosine phi, y is r sine phi, so I have introduced polar coordinates in the xy plane, and I have related z with t via an exponential. We also need to have the inverse, so we need to express r, phi, and t in terms of x, y, and z. And Sage doesn't do this automatically, so I have to tell Sage explicitly also the inverse transition map. You can compute it using the solve function, so you might solve this system for r, phi, and t, but still you will have to tell Sage explicitly the inverse function. So I solved it and inserted in here. So r is given in terms of the x and y coordinates, phi is given in terms of the x and y coordinates, and t is given in terms of the z coordinate. So that is the set inverse method which I'm applying. And if I do that, then Sage checks whether these two transition maps are really inverse to of one another. And it checks that, and so it composes the two maps and checks if you get the identity. And you see everywhere here is a pass, so it says that's fine, except there's one failed here. But this does not necessarily mean that you made a mistake when you set the inverse function. It just means that Sage is not able to simplify the result sufficiently to identify it with phi. So even if there is a failed, this can be just due to a mere lack of simplification, like in this case. Okay, so here is the inverse transition map now, where we express r, phi, and t in terms of x, y, and z. Okay, so far we have three charts on our manifold M, namely the original chart with the standard chart with coordinate functions x, y, and z, its restriction to the subset U, also with functions x, y, and z, and the polar coordinates, if you like, on the also on this open subset U. And the first chart that we defined is considered as the default chart. This means that when I express things later and I do not specify the chart, then the default chart will be taken. So M with x and y and z coordinates are the default chart. It can be changed, so if you want to have everything expressed in some other chart, you can use the method set default chart to change the default chart if you want. The subset U is an open subset of the manifold, so it's a manifold in its own right, and therefore it also has an atlas. And in fact, here we have only two charts, namely U with the standard coordinates and U with polar coordinates. And the one that we defined first is the default chart for that one, so which is U and with the coordinates X and Y and Z. Okay, sometimes it's nice to plot the coordinate lines of one chart in terms of the coordinates of another chart to get some visual impression of how the transition map works. So we can do that here. So let's use the plot command to compare the standard chart and the polar chart. And here we see, so the coordinate lines of the polar coordinates are expressed in terms of the standard coordinates. So you see here the coordinate lines of the theta variable, and here the coordinate lines of the r variable, and this is the coordinate lines of the t variable, and it's stretched because we have this exponential here. All right, now manifold is in particular a set, and so we can have points on that manifold. So let's declare a point of the manifold. So we apply the method point, m.point. This declares a point of the manifold M. The Python variable is p. The mathematical name is also put to p here. And which point am I declaring? Well, I'm telling Sage with respect to the standard chart, the coordinates should be 1, 2, 1. So that's the point that I'm declaring. P is the point on the manifold which has coordinates 1 to 1 with respect to the STD chart. Question, is this point contained in the open subset U? Well, let's ask Sage. Yes, it is. So we can also ask for the polar coordinates of this point. So if I call the standard chart on P, then I get the coordinates 1 to 1, which is of course exactly what I defined here. But I can also ask for the coordinates of P in the other chart, and here is the result. So that makes sense because P is in the subset U on which the polar chart is defined. Now let's come to scalar fields on the manifold. This is not to be confused with the functions that we have defined earlier. The functions that we defined earlier are functions of the coordinates. So they are functions of triples of numbers in this case. Whereas scalar fields are maps from the manifold M itself to reals. So this is a map that takes as its argument points and not coordinate tuples. Okay, so let's declare it. So I'm declaring F to be a scalar field on the manifold M. And which scalar field should it be? Well, I tell Sage that with respect to the standard chart, the scalar field should be given by this expression x plus y squared plus z cubed. And the mathematical name should also be F. Okay, so let's do that. And since F is now a scalar field on M, so a function on M and not on coordinate domains or codomains, then I can evaluate it on points. And if I do that for the point that I defined above, then I get the number 6 in this case. We can display the function with respect to our charts. So for the standard chart, of course, this is exactly what we have used to define it. But in the polar chart, we can also express it. This is now valid only on U and is given by this expression. So, this mathematical formula of this mathematical transform has automatically been performed by Sage. All right. The underlying expression can also be retrieved from the scalar field by the XPR method. So with respect to the standard chart, we get the expression that we used to define the scalar field. And if I do this for the polar chart, I get the corresponding expression in terms of r, phi, and t. We can also define a scalar field by some unspecified function of some coordinates. So let's define a scalar field h with the mathematical name h by an unspecified function capital H applied to the standard coordinates x, y, and z. So then we see we have this scalar field in standard coordinates x, y, and z. This gives the value h of x, y, and z. And in polar coordinates, we have to insert the correspondingly transformed expressions of the polar coordinates in our function capital H. Also, such a function can be evaluated on a point, and then one would get capital H of 1 to 1 for the point that we declared earlier. Many arithmetic operations can be done on scalar fields. For example, we can form linear combinations. So let's take the linear combination f plus 2 times h. This gives me a new scalar field, which is called s here, and let's display it, let's say in polar coordinates, and that would be the result that we get. Okay, so we have seen how to define a manifold, how to declare charts, how to relate various charts to one another, how to define functions defined on coordinate variables, how to define scalar fields, which are actually functions on the manifold itself. In the next video, we will treat vector fields, and hope to see you again.